Welcome to this tutorial on model-based design for quadcopter autopilot, from concept to prototype. Here is the outline of this tutorial. In this session, we will design and implement the inertial sensor fusion algorithms in MATLAB to estimate orientation, combining data from gyroscopes, accelerometers, and magnetometers. In this session, we'll discuss why inertial sensor fusion is essential and how to implement it in MATLAB using methods like the Complementary Filter, imufilter, AHRS, as well as the Madgwick and Mahoney algorithms. We will begin by illustrating why sensor fusion is essential. To demonstrate the sensor fusion algorithms, we will use real-world data. For live sensor data acquisition, we will leverage the MATLAB mobile app, which streams data directly from your mobile phone's inertial sensors into MATLAB. Let's get started from the gyroscope. A gyroscope measures angular velocity, how fast an object is rotating around its axes. It provides accurate short-term rotation data, responds rapidly to quick movements, and less affected by linear motion or external disturbances. However, gyroscope suffers from drift over time due to sensor bias. As a result, it requires calibration and filtering to maintain long-term accuracy and stability. To begin the demonstration, we'll first connect MATLAB to a mobile phone using the MATLAB mobile app. As an initial step, we'll remove the constant bias of the gyroscope by placing the phone stationary on a table and logging data while it remains still. This allows us to estimate and subtract the static bias from subsequent measurements. Next, we will estimate the device's orientation, specifically the roll, pitch, and yaw angles, by integrating the gyroscope readings over time. This approach provides a simple way to track rotational motion, but it can accumulate drift without correction. This figure shows that over a short period, for example 60 seconds, the gyroscope exhibits low noise, making it reliable for short-term motion tracking. However, over longer durations, for example 600 seconds, even small biases can accumulate, leading to significant drift, highlighting the need for sensor fusion. An accelerometer measures linear acceleration, and when the device is stationary, it can estimate orientation by sensing the direction of gravity, useful for determining roll and pitch. It's low cost, low power, and provides an absolute reference without long-term drift. However, it is sensitive to motion and vibrations, where the acceleration no longer reflects gravity alone. To begin the demonstration, we'll first connect MATLAB to a mobile phone using the MATLAB mobile app. We then log accelerometer data while rotating the device along the roll and pitch axes. To simulate external disturbances, we also tap the device with a pen, generating pulse-like measurements. The figure below shows the raw accelerometer data along the three axes. Next, we'll use this data to estimate the device's orientation, focusing on the roll and pitch angle. We can observe that estimating orientation using the accelerometer alone provides accurate results over long periods, but tends to be noisy and unreliable in the short term, especially during motion or sudden disturbances. That's why sensor fusion is essential. It allows us to combine the strengths of different sensors, using their complementary characteristics to achieve accurate and reliable orientation estimates. Next, we'll demonstrate how to perform sensor fusion in MATLAB by combining data from the gyroscope, accelerometer, and magnetometer to estimate orientation. We will walk through several sensor fusion methods in MATLAB, starting with the Complementary Filter and imufilter, which combine gyroscope and accelerometer data. Then we'll explore orientation estimation using the Complementary Filter with magnetometer, as well as the AHRS filter, Madgwick and Mahoney algorithms. Let's begin with the complementary filter. The complementary filter is a simple and intuitive method for combining gyroscope and accelerometer data to estimate orientation. It takes advantage of the strengths of both sensors while compensating for their weaknesses. The gyroscope provides smooth and responsive measurements of angular velocity, which can be integrated over time to estimate orientation. However, it suffers from drift due to bias and noise. To address this, a high-pass filter is applied to the gyroscope data. This allows the filter to retain fast, short-term changes in motion while attenuating long-term drift. On the other hand, the accelerometer provides an absolute reference by sensing the direction of gravity. It is stable over time but susceptible to short-term noise and disturbances during movement. Therefore, a low-pass filter is applied to the accelerometer data, allowing it to contribute reliable long-term information while filtering out rapid fluctuations. The complementary filter blends these two filtered signals, high-frequency data from the gyroscope and low-frequency data from the accelerometer, to produce an orientation estimate that is both responsive and stable. To begin the demonstration, we'll first connect MATLAB to a mobile phone and remove the constant bias of the gyroscope by placing the phone stationary on a table. Next, we log both gyroscope and accelerometer data while rotating the device along the roll, pitch, and yaw axes. We then estimate the device's orientation, roll, pitch, and yaw angles using the complementary filter, which fuses the short-term precision of the gyroscope with the long-term stability of the accelerometer. The performance of the filter depends on properly tuning the gain, which determines how much weight is given to each sensor. A higher gain emphasizes gyroscope data for responsiveness, while a lower gain relies more on accelerometer data for stability. The figures show the results of the complementary filter. As you can see, the estimated orientation angles fit quite well with the ground truth, demonstrating that the filter provides a good balance between the responsiveness of the gyroscope and the stability of the accelerometer. Now that we've gone through the complementary filter, let's move on to the imufilter provided by the Sensor Fusion and Tracking Toolbox in MATLAB. The imufilter in MATLAB uses a 6-axis indirect Kalman filter, which tracks errors in orientation, gyroscope bias, and linear acceleration rather than estimating orientation directly. It predicts orientation using gyroscope data and then corrects it by comparing the measured gravity vector from the accelerometer with the expected gravity based on the current estimate. By modeling small error states and applying a Kalman gain, the filter effectively reduces gyroscope drift while maintaining robustness to motion and noise. To begin the demonstration, we first connect MATLAB to a mobile phone and remove the constant gyroscope bias by placing the phone stationary on a table. Next, we log gyroscope and accelerometer data while rotating the device along the roll, pitch, and yaw axes. We then estimate the device's orientation, roll, pitch, and yaw angles using the imufilter from the Sensor Fusion and Tracking Toolbox. To improve accuracy, we can use the filter's automatic tuning feature to optimize its parameters based on the sensor data and ground truth. After tuning, we rerun the fusion process to obtain more accurate orientation estimates. The figures show the results of the IMU filter. As shown, the estimated orientation angles closely match the ground truth, demonstrating that the filter delivers accurate and reliable performance after sensor fusion. Now that we've covered filters using only the gyroscope and accelerometer, let's move on to incorporating the magnetometer for full 3D orientation estimation, including yaw. We'll begin by revisiting the complementary filter, this time fusing data from all 3 sensors: gyroscope, accelerometer, and magnetometer. The complementary filter can be extended to fuse data from the gyroscope, accelerometer, and magnetometer to estimate full 3D orientation, roll, pitch, and yaw. The gyroscope provides smooth, short-term angular velocity measurements, but suffers from drift over time. The accelerometer offers a stable estimate of the gravity vector, helping to correct roll and pitch. The magnetometer provides a reference to the Earth's magnetic field, helping to correct yaw, which neither the gyroscope nor accelerometer can reliably do over long periods. In this setup, the filter applies a high-pass filter to the gyroscope data to retain fast, short-term motion, and a low-pass filter to the accelerometer and magnetometer data to provide long-term stability and correct drift. By blending all three sensor types, the complementary filter produces an orientation estimate that is both responsive and stable across all three axes. To begin the demonstration, we first connect MATLAB to a mobile phone and remove the constant bias of the gyroscope by placing the phone stationary on a table. Next, we log gyroscope, accelerometer, and magnetometer data while rotating the device along the roll, pitch, and yaw axes. We then estimate the device's orientation, roll, pitch, and yaw angles, using the complementary filter, which fuses the short-term accuracy of the gyroscope with the long-term stability of the accelerometer and corrects yaw drift using the magnetometer. The filter's performance depends on tuning the gain, which controls how much influence each sensor has. A higher gain favors gyroscope data for responsiveness, while a lower gain gives more weight to the accelerometer and magnetometer for stability and drift correction. Using the complementary filter, we observe that the yaw angle estimation shows a noticeable bias. This is likely caused by an uncalibrated magnetometer or magnetic disturbances in the environment, such as nearby electronics or metallic objects. Unlike roll and pitch, which are accurately estimated using the accelerometer and gyroscope, yaw relies heavily on magnetometer data for heading correction. If the magnetometer is miscalibrated or affected by interference, the yaw estimate can drift or show a consistent offset. This highlights the importance of proper magnetometer calibration and operating in a magnetically clean environment for reliable full orientation tracking. Now that we've gone through the complementary filter, let's move on to the AHRS filter provided by the Sensor Fusion and Tracking Toolbox in MATLAB. The AHRS filter in MATLAB's Sensor Fusion and Tracking Toolbox uses a multiplicative extended Kalman filter to estimate device orientation from gyroscope, accelerometer, and magnetometer data. It predicts orientation using gyroscope integration and then corrects errors using accelerometer measurements for roll and pitch and magnetometer measurements for yaw. Instead of directly updating the quaternion, the filter estimates a small error quaternion, preserving numerical stability and unit norm. It also tracks gyroscope bias to reduce long-term drift, resulting in a robust drift-compensated 3D orientation estimate. To begin the demonstration, we first connect MATLAB to a mobile phone and remove the constant gyroscope bias by placing the phone stationary on a table. Next, we record gyroscope, accelerometer, and magnetometer data while rotating the device along the roll, pitch, and yaw axes. We then estimate the device's orientation, roll, pitch, and yaw angles using the AHRS filter from the Sensor Fusion and Tracking Toolbox, which combines all three sensor inputs for drift-compensated 3D orientation. To enhance accuracy, we apply the filter's automatic tuning feature to optimize parameters using the recorded sensor data and ground truth. After tuning, we rerun the fusion process to obtain more precise and reliable orientation estimates. The figures show the results of the tuned AHRS filter. As illustrated, the estimated orientation angles match the ground truth, demonstrating that the filter provides accurate and reliable performance after sensor fusion. Now that we've covered the AHRS filter, let's move on to the Madgwick filter in MATLAB, another widely used algorithm for real-time orientation estimation using inertial and magnetic sensors. The Madgwick and Mahoney AHRS algorithms are open source, and their MATLAB implementations and documentations can be downloaded from the web page. The Madgwick algorithm is a computationally efficient sensor fusion method designed for real-time orientation estimation using data from a gyroscope, accelerometer, and optionally a magnetometer. It uses a gradient descent optimization approach to minimize the error between measured and estimated directions of gravity and magnetic field. The gyroscope provides short-term angular velocity, while the accelerometer and magnetometer correct for drift by aligning the orientation estimate with gravity and magnetic north. The algorithm updates the orientation represented as a quaternion, offering a good balance between accuracy and performance, especially for embedded and real-time systems. To begin the demonstration, we first connect MATLAB to a mobile phone and remove the constant gyroscope bias by placing the phone stationary on a table. Next, we record gyroscope, accelerometer, and magnetometer data while rotating the device along the roll, pitch, and yaw axes. We then estimate the device's orientation, roll, pitch, and yaw angles using the Madgwick algorithm, which fuses all three sensor inputs to provide drift-compensated 3D orientation. To improve accuracy, we can fine-tune the algorithm by adjusting the gain parameter beta, which controls how strongly the filter corrects orientation based on accelerometer and magnetometer feedback. The figures show the results of the Madgwick algorithm. As illustrated, the estimated orientation angles align closely with the ground truth, demonstrating that the filter delivers accurate and reliable performance in fusing inertial and magnetic sensor data. Now that we've covered the Madgwick algorithm, let's move on to the Mahoney algorithm, another popular open-source filter for fusing gyroscope, accelerometer, and magnetometer data to estimate orientation. The Mahoney algorithm is a sensor fusion method for estimating orientation using gyroscope, accelerometer, and optionally magnetometer data. It operates using a nonlinear complementary filter that blends high-frequency gyroscope data with low-frequency accelerometer and magnetometer measurements to correct for drift. The algorithm introduces a proportional integral PI feedback loop to minimize orientation error by comparing the measured and estimated gravity and magnetic vectors. Orientation is maintained using quaternion representation, and the integral term helps compensate for long-term bias in the gyroscope. Mahoney's filter is known for being lightweight and effective, making it well-suited for embedded applications. To begin the demonstration, we first connect MATLAB to a mobile phone and remove the constant gyroscope bias by placing the phone stationary on a table. Next, we record gyroscope, accelerometer, and magnetometer data while rotating the device along the roll, pitch, and yaw axes. We then estimate the device's orientation, roll, pitch, and yaw angles using the Mahoney algorithm, which fuses all three sensor inputs to compute drift-compensated 3D orientation. To improve accuracy, we can fine-tune the algorithm by adjusting its proportional gain, Kp, and integral gain, Ki. The Kp parameter determines how strongly the filter responds to orientation errors, helping correct deviations quickly. The Ki parameter compensates for long-term drift by integrating the error over time, effectively correcting steady-state bias in the gyroscope. The figures show the results of the Mahoney algorithm. As illustrated, the estimated orientation angles align closely with the ground truth, demonstrating the algorithm's ability to provide accurate and stable orientation estimates when properly tuned. To summarize, the complementary filter fuses gyroscope, accelerometer, and magnetometer data by blending short-term gyroscope accuracy with long-term sensor stability. It's simple but needs manual gain tuning. The imufilter uses a Kalman filter approach to estimate orientation and correct gyroscope drift, offering good accuracy with optional automatic tuning. The AHRS filter is also based on an extended Kalman filter, but incorporates magnetometer data for full 3D orientation. The Madgwick algorithm uses gradient descent for efficient drift-corrected orientation with a tunable gain, beta, while the Mahoney algorithm applies feedback control with proportional, Kp, and integral, Ki gains to balance responsiveness and stability. Let's return to our quadcopter model. In session 6, we created a virtual IMU sensor in Simulink to simulate gyroscope, accelerometer, and magnetometer outputs. In this session, we'll build sensor fusion blocks in Simulink to estimate the quadcopter's orientation using these virtual sensor signals. Simulink provides several sensor fusion blocks in the sensor fusion and tracking toolbox. The IMU filter block uses a Kalman filter to fuse gyroscope and accelerometer data for drift-corrected orientation. The complementary filter block blends sensor data using a simple weighted approach, balancing short-term gyroscope accuracy with long-term stability. The AHRS block uses an extended Kalman filter to fuse gyroscope, accelerometer, and magnetometer data for accurate 3D orientation estimation. To begin the demonstration, we first run the simulation of a quadcopter following a predefined trajectory. During the flight, we record the gyroscope, accelerometer, and magnetometer data, along with the estimated orientation angles. We then visualize and analyze the results using the Simulation Data Inspector in Simulink. Some of the results may not look accurate because the filter parameters have not been fine-tuned yet. We can also demonstrate sensor fusion using the recorded simulation data in MATLAB. In this example, we apply the complementary filter to fuse gyroscope and accelerometer data. The results show that the estimated orientation angles align closely with the ground truth. In addition to the sensor fusion algorithms we have demonstrated, there are several other filtering methods available, each with its own strengths and application scenarios. This table summarizes these additional filters, outlining their inputs, outputs, and key characteristics to help guide the selection of the most suitable algorithm for your system. All right, let's wrap up this session. We've explored several inertial sensor fusion algorithms in both MATLAB and Simulink, including the complementary filter, IMU filter, AHRS filter, as well as the Madgwick and Mahoney algorithms. I hope this session has helped you understand the importance of sensor fusion and how to implement it effectively using MATLAB and Simulink. In the next session, we will focus on the validating requirements and system design. I look forward to your participation.